Do you ever discover one of those subjects within software development or computer science that just seems like it's too good to be true? Concurrency is one of those things. If I told you, hey, instead of writing a program just top to bottom that runs each individual command before it runs the next command, you would say, well, yeah, that's how you do all software development. There is a different way, and it's honestly how most modern software works behind the scenes. It's called concurrency. Essentially, what concurrency is you have one main thread of execution that starts multiple other threads of execution that do individual pieces of work. Now, that sounds simple. That sounds easily maintainable. That sounds like a great feature because essentially what you're using is multiple cores within your GPU or within your CPU, sorry, which has multiple cores. If you have any kind of like desktop or laptop that's been built over the last like 20 years, you're probably going to have a multi-core processor. That multi-core processor can run multiple threads of execution at a time. You're going to want to take advantage of that. And again, your programs are taking advantage of that behind the scenes. You just don't see it yet. What concurrency allows you to do is, let's say you've got 4 batches of work, you can run all 4 batches of work at the exact same time. There are caveats. As I mentioned in the blog post, which I will link below, there are tons of edge cases and tons of issues that you run into when you start using concurrency within your programs. Golang allows you to do concurrency very, very easily using literally a 2-letter keyword. That is the Goroutine keyword. So we're going to talk a little bit about Goroutines today. And when I say a little bit, I really do mean a little bit. We're going to cover one incredibly obvious edge case or bug that Goroutines can cause, or that concurrency just in general can cause. And we're going to show kind of different hacky ways to get around it to kind of display what concurrency is all about. So let's take a look at a very simple program. Again, I've already written this program because I've already written a blog about it. If you would rather read over the blog, it'll have all of the code and all of that within the blog that you can copy and paste and play around with. Basically, what we're doing here is we are simulating an API endpoint that is doing some work. This work we're just going to kind of, we're essentially just going to simulate it using a sleep function. So each individual call to this get handler function is going to pass an offset. That offset is going to be used to determine how long you're going to sleep within this function call. So we've got 5 calls to this function. This function is going to print out a route, and it's going to print out a message after it sleeps. So if we run this, we're going to get something very expected. Essentially, it's going to wait for 2 plus 4 plus 8 plus 16 plus 32, which would be 62 seconds. I did the math behind the scenes. And then it is going to print out the total runtime. We will expect it to run for 62 seconds. It is going to call this, finish, call this, finish, call this, finish, call this, finish, call this, finish. This is how you write most programs. This is the way you're used to running programs. So let's go ahead and run this. So we see it starts here. It hits route 1. Route 1 only waits for 2 seconds. It prints out the message. Route 2 waits for 4 seconds, prints out the message. Route 3 waits for 8 seconds. So we're going to have a little bit of a lag time, and I'm going to have to figure out a way to fill this empty space with me talking about something, finishes that message. And then this one is going to run for 16 seconds, and then we're going to have one that runs for 32 seconds. Probably should have chosen shorter offset periods for this since I'm recording now. But we can wait another 32 seconds for Route 5 to finish. And the purpose of this is really just to prove that I'm not doing any magic behind the scenes aside from using Goroutines here in a second to kind of display how magical this can be. Now, I am going to go ahead and shorten these. So let's make this 16 seconds. Let's make this 8 seconds, 4 seconds, 3 seconds. We'll just do it that way. Let's shorten that by a little bit. So as we expected, the total runtime was 62 seconds long. Again, it is just all of these offsets added up, or the previous offsets, I guess. Now let's add Goroutines. Now I'm not going to explain the magic again while I'm, kind of displaying this. I'm just going to go ahead and add this go keyword. And what this does, I guess I will explain the magic again. What this does is as soon as it hits this go keyword, it's going to create a new thread of execution that is going to execute this function call. And then it's going to go to the next line, and it's going to create another thread of execution that is going to execute this function call. And then it goes to the next line, creates another thread of execution, and executes this function call. Now, critically, you still maintain that main thread of execution here. So the next line is going to get run within the main thread of execution. And once that one's done, then it's going to run this thread of execution. These are not going to continue and run the rest of the main function on their own. You're not going to run into those issues that you might see within, C, C++. You probably can create those problems, but it would take a little bit more work. And honestly, my brain is too fried to think about how you would do that. So these three right here are going to be executed in three separate threads of execution. What you're going to see immediately is a race condition bug, or what could be a race condition bug if the context of your program basically creates that race condition bug. That sounds confusing, but we'll cover race conditions later on. But what you're going to see is everything's going to be executed in kind of a weird order, or maybe it's not. It's kind of unpredictable, but essentially everything can get executed in a weird order. And once we run this, we see immediately route 4, 1, 3, 2. Everything's out of order here because all of these are being, run concurrently, and then route 4 is being run immediately. And again, everything is, fairly out of order here. But what we'll see at the very end is what can kind of be deceiving. We would expect this to run in 5, 9, 17, so like 33 seconds-ish, something like that. It ran in 24. So if we pull up our handy-dandy calculator, 24 divided by 33 times 100, so roughly 72% faster, or 72% of the time that we expected. That's pretty damn fast. That's significantly faster than we expected. So let's display a very, very simple bug that you can get if you start to get greedy here. We can actually see it before we implement the full bug, but we're going to implement the full bug here. So what if we decided to run all of these function calls within their own threads of execution? In your brain, because you've seen, we've just decreased the runtime by 28% just by adding 8 letters to our code, or 6 letters to our code, sorry. You might say, okay, well, let's just throw everything in its own thread. Let's just completely, destroy our CPU, depending on how much work this is actually doing. Let's just completely destroy our CPU and throw everything into its own thread of execution, because that's going to make it run wicked fast. Well, let's see if that's the case. That's actually running better than I expected. Oh, I didn't save. Okay. I was like, that's not supposed to happen. All right, let's try this again. And we get a runtime of 0 seconds. We had just enough time to print the first line within Route 3 and Route 1, which, if you run this again, you're probably going to get, a completely different run, and you'll get a completely different run. So what's happening here? So you've got your main thread of execution that is creating these 5 individual threads of execution. It is then calculating your end time, it's printing that, and then that main thread of execution ends. That is critical to understand here. After main has finished executing all of the things that it needs to execute, main ends. And when main ends, all of those Goroutines, all of those separate threads of execution are headless, or they end right there. It just gets cleaned up and thrown away. So if you start to get greedy, then you can run into some unforeseen circumstances here. Let's see what happens if we throw this out. We might get it, it might run normally, it might not run normally. So we've hit the end of 1, 2, 3. We've started 5, hit 4. This might actually run fine. So that one ran fine. I think that was just kind of how the offsets worked. But if we do it this way, then we're going to run into issues. 4, 1, 2, 3, hit route 1, route 2, route 3, and route 4, but it did not print out that message from route 5. That's because before route 5 was able to start running and finish running, route 4 ended here, and then it ran route 5, and then main thread ended. So, like I said, concurrency is often treated by folks who are new to computer science, or folks who are new to the idea of concurrency as like free efficiency. You just throw concurrency at a problem. It's, another like kind of similar solution to this is parallelism, which is a similar but different thing. They think you just throw Goroutines at a problem and it magically makes everything a bajillion times faster with no cost. And we're not even talking about CPU time cost, because there's that cost as well. But people think, you just throw concurrency at a problem and, done. I've just made my code like, 28% faster just overnight. And yes, you can make it faster that way. But if you don't orchestrate things and if you don't set things up in a way that handles concurrency and handles all of the edge cases that can occur and all of the race conditions that can occur and all of the issues that can arise with concurrency, you're going to run into some very serious bugs that can cause unforeseen and almost unfixable bugs in your code. One of the issues that comes with concurrent code and with parallel code oftentimes is added complexity where you really don't need it. Unless you have a use case that not just can use concurrency but should use concurrency and is well benefited to concurrency, then you probably shouldn't add it into your code. Now, this was a high level kind of quick example of what concurrency can look like. It was a very, very oversimplified example, just like a lot of example tutorials are. We're going to go a little bit more in depth on how you can handle concurrency and how you can handle some of these bugs and how concurrency can help you in certain circumstances later on. But I did want to introduce the idea of concurrency and some very quick and easy bugs that you can get whenever you just throw concurrency at a problem expecting it to solve, all of your issues. So that's really about it. If you enjoyed this, it's a little bit more in the computer science-y area. If you enjoyed it, let me know. Take it easy. Peace.